No one thinks a nation would melt down thousands of tons of real silver, the same silver used in jewelry, just to build a weapon. But the United States did exactly that. 14,700 tons. The Treasury office fell silent after Nichols' request. 6,000 tons of silver wasn't a large order. It was an absurdity. A number so big it didn't fit inside anyone's head. Not Bell's, not Nichols', not anyone's. Bell leaned back slowly, studying the young officer standing in front of him. Nichols didn't look nervous. He didn't look unsure. He looked like a man who'd already accepted that the request was insane, but also accepted that it had to be done. Bell finally spoke. 6,000 tons. How many troy ounces is that? Nichols didn't blink. Sir, I don't know. It was one of those moments where two people, both competent and experienced, realized they had stumbled into something completely outside normal life. The Treasury thought in troy ounces, precise, delicate units used for precious metals. Nichols thought in tons, engineering mass, industrial weight, war-scale quantities. Two worlds, one room, zero overlap. Bell's face tightened. Young man, the Treasury will always think in troy ounces. Nichols didn't argue. He couldn't. He couldn't tell Bell that the metal wasn't going to coins, or wires, or weapons anyone could recognize. The truth was too sensitive. The project he represented was so classified that not even the man guarding the nation's wealth was allowed to know its name. So Nichols simply repeated the only number he was allowed to say, 6,000 tons. Then he added, quietly but firmly, "We need it immediately." Bell stared at him. Requests this size usually took weeks, months to process. But there was something in Nichols' voice, something that made the request feel less like a proposal and more like an inevitability. Bell didn't know the details, but he understood one thing with perfect clarity. Whatever this project was, it was bigger than him, bigger than the Treasury, bigger than everything happening outside that room. He took a breath and said, "All right, we'll approve the transfer." But the meeting wasn't over. As final plans came in, the numbers shifted. Engineers recalculated. Designs expanded. Prototypes grew larger. Racetrack layouts multiplied. 6,000 tons wasn't enough. 7,000 wasn't enough. 10,000 wasn't enough. The true requirement, the real, final number was 14,700 tons of silver. Silver that would be melted, extruded, shaped into massive coils, and locked inside magnets the size of small buildings. This wasn't Treasury silver anymore. It wasn't money. It wasn't reserve. It was about to become part of a machine so far outside normal imagination that almost no one alive at the time could have understood it. A machine designed to do something that had never been attempted at industrial scale. Separate uranium-235 from uranium-238. Two atoms identical in every way, except for 3 neutrons. That tiny difference would determine whether the Allies built an atomic bomb or lost the race entirely. And it all began with a bizarre morning in a quiet Washington office, a confused conversation about troy ounces, and a request that should have been impossible, but wasn't. Because the Manhattan Project didn't need permission, it needed results. And on that day, the United States Treasury handed over the first piece of a secret that would reshape the end of the war. The silver request was only the first crack in a much larger story. To understand why the United States was willing to melt thousands of tons of precious metal, you have to understand the problem that pushed them into desperation, a problem so simple to describe, yet so brutally difficult to solve, that most scientists at the time believed it was effectively impossible. The Manhattan Project's physicists already knew the basic truth. If you want an atomic bomb, you need uranium-235. If you don't have uranium-235, you don't have a bomb. It was that simple. There was just one issue. In nature, uranium-235 makes up 72% of all uranium. Not even 1%. The other 28% is uranium-238, almost identical in every chemical way, but utterly useless for sustaining a nuclear chain reaction. To a chemist, U-235 and U-238 are twins. Same electrons, same proton count, same chemical behavior, same everything. Their only difference? 3 neutrons. U-235 has 143. U-238 has 146. 3 neutrons, that's it. A difference so tiny a human couldn't possibly see it, even with a microscope. Yet those 3 neutrons separate ordinary metal from the core of a weapon that could end the war. We have the ground. Why says the Manhattan Project needed uranium that was 90% U-235 or better. But how do you take a pile of uranium, where only a fraction of a percent is useful, and separate the good atoms from the useless ones? There was no manual for this. There was no known method. There was no machinery on Earth built for this purpose. Every nation in the world was facing the same riddle. Most believed it couldn't be solved in time to matter. Scientists proposed several paths. Gaseous diffusion, incredible complexity, almost impossible to scale yet. Thermal diffusion, promising in theory, unstable in practice. Centrifuges, elegant but fragile, unreliable, and years away from mass production. The United States simply didn't have years. Hitler's teams in Europe were also racing toward a bomb, and no one knew how far they had progressed. That was when a different kind of solution surfaced, not elegant, not clean, not efficient, not even sane, but perhaps fast enough to work. The idea came from a man who refused to accept that the impossible was truly impossible. Ernest Lawrence, the brilliant and relentless physicist from the University of California, Berkeley. Lawrence had already changed the world once by inventing the cyclotron, a circular particle accelerator that smashed atoms by whipping them around a magnetic field. He wasn't afraid of big ideas. He wasn't afraid of pushing machines beyond their limits. And he wasn't afraid to scale something to absurd proportions if the physics said it might work. In 1941, British physicist Mark Oliphant visited Lawrence and delivered a message from Britain's atomic research committees. A bomb is possible, but only if we can get enriched uranium, and quickly. That message ignited Lawrence's imagination. He believed that the principle behind his cyclotron bending charged particles through magnetic fields could be pushed further. What if, instead of smashing atoms, they separated them? What if they ionized uranium, gave each atom an electric charge, and shot it through a powerful magnetic field? Lighter U-235 atoms would curve slightly more. Heavier U-238 atoms would curve slightly less. Different mass, different paths. Catch them in separate collectors, and you've just solved the problem. A mass spectrometer, but scaled up to industrial size, far bigger than anyone had ever attempted. It was bold. It was untested. It sounded insane. But Lawrence built a prototype anyway. He converted his 37-inch cyclotron into an experimental separation machine, the first Calutron. And on December 2nd, 1941, 5 days before Pearl Harbor, he powered it on. It worked. Not well. Not efficiently. Not fast. But it worked. By January 1942, the crude prototype had produced 18 micrograms, enriched to 25%, 10 times more enrichment than any method before it. To most scientists, this was nowhere near enough. To Lawrence, it was proof. Proof that the principle was sound. Proof that it could work on a larger scale. Proof that, with enough machines and enough power, the United States could beat the clock. But there was a problem hiding inside the success. Scaling a tabletop machine into hundreds of industrial calutrons would require something enormous magnets so large, so powerful, so hungry for conductive metal that no factory in America had the copper to build them. The prototype had worked, and now it threatened to collapse under its own success. The United States didn't have the copper, but the project had already crossed a point of no return. And that is why, in the coming months, engineers would be forced into one of the strangest decisions in the history of warfare, a decision that would send Kenneth Nichols back into the Treasury, this time asking for far more than 6,000 tons of silver. The Manhattan Project had a problem that was growing more urgent by the day. The prototype Calutron had proved the concept barely. It showed that uranium atoms could be separated by mass using magnetic fields. But that small victory created a massive new crisis. If this process was going to save the project, It had to be scaled up to a level no one had ever attempted. And the only man who truly believed it was possible was Ernest Orlando Lawrence. Lawrence was not a typical academic. He was a builder, a machine-obsessed genius who believed that if physics allowed something in principle, then engineering should make it real, no matter the size, cost, or complexity. His lab at Berkeley was famous for machines that began small and then grew larger, heavier, louder, and more dangerous with each revision. He believed in physics the way some men believe in destiny. When Mark Oliphant arrived from Britain in 1941, Lawrence listened intently as the visiting physicist explained the findings of the British Maud Committee. A nuclear bomb was possible. It would require uranium-235, and whoever produced enriched uranium first would win a decisive advantage in the war. Most scientists received that message with caution. Lawrence received it like a challenge. His mind jumped instantly to the cyclotron, his own creation. Cyclotrons flung charged particles through magnetic fields. Mass determined how sharply the particles bent. He had used that principle for years, guiding beams of ions into targets. What if that same principle, the simple physics of heavier curves less, lighter curves more, was the key to separating U-235 from U-238? To anyone else, it sounded ludicrous. To Lawrence, it sounded obvious. He wasted no time. He ordered his 37-inch cyclotron stripped and modified. He pushed his team to work day and night not because he had proof it would work, but because he believed the physics was too clean, too elegant, to be wrong. On December 2nd, 1941, just 5 days before Pearl Harbor would plunge the United States into the war, the modified machine was switched on. A thin beam of ionized uranium passed through the powerful magnet. On the far side, in the narrow collector cups, tiny traces of uranium settled heavier atoms on one path, lighter on another. The machine had worked. The team measured the yield. 5 microamperes collected. Then, by January 1942, they reached 18 micrograms of uranium, enriched to 25%, 10 times more than any previous method on Earth. It was microscopic. It was nothing close to what a bomb required. But it was a door that had been closed to every other method. Lawrence saw that door and declared it wide open. He immediately began sketching designs for machines far larger than the prototype. He imagined rooms lined with calutrons, racetracks of magnets bending beams of uranium day and night, hundreds of vacuum tanks, miles of coils, massive power supplies. Where others saw a fragile, experimental device, Lawrence saw an entire factory, one that could turn raw uranium into a weapon. The higher-ups in the Manhattan Project listened. Slowly, the impossible idea began turning into a plan. But then came the harsh reality. To build a single large Calutron magnet, just one, the engineers needed an enormous amount of conductive metal. The coils had to be huge, tightly wound, and perfectly pure. And the prototype had already shown that even small magnets required massive copper windings. Project planners did the math. To build hundreds of calutrons, arranged in multiple racetracks operating continuously, the project would require 5,000 short tons of copper, and that was only the minimum estimate. 5,000 tons of copper. In 1942, copper was the bloodstream of the war. Ships, planes, tanks, artillery, radios, radar, ammunition casings, communications, cables, every branch of the military was fighting for it. Even essential civilian industries couldn't get enough copper. But Lawrence's idea didn't care about shortages. The physics didn't bend for logistics. The machine was either built to the required scale, or it wasn't worth building at all. And that's when the Manhattan Project's engineers realized they were at an impossible crossroads. Either find a way to replace 5,000 tons of copper, or watch Lawrence's only working uranium separation method die before it ever began. The answer they found would be one of the strangest, boldest decisions in American industrial history. And it would send Lieutenant Colonel Kenneth Nichols straight back into the Treasury, this time not for 6,000 tons, but for nearly 15,000. The moment Lawrence proved his Calutron could separate uranium, the Manhattan Project gained something priceless: a working method. But with that breakthrough came a brutal truth. A single Calutron was useless. To get even one bomb's worth of enriched uranium, the United States would need hundreds of them, all operating around the clock. That meant magnets. Gigantic magnets. Magnets far larger than anything ever built. Because a Calutron wasn't a tidy laboratory device. It was a monster. A hulking vacuum tank surrounded by massive coils that had to generate magnetic fields strong enough to bend uranium atoms into separate arcs. And those coils needed metal. A staggering amount of metal. Copper was the natural choice. It was the best practical conductor available on Earth, cheap enough, ductile enough, and able to handle high current without catastrophic loss. So, Colonel James Marshall and Lieutenant Colonel Kenneth Nichols did what every good engineer does. They asked, "How much copper do we need?" Everyone. The answer hit like a punch. To build the Calutrons for the WWII electromagnetic plant at Oak Ridge, they would need 5,000 short tons of copper. 5,000 tons. Just for the magnet windings. No factory in the United States had that copper. No supply chain could produce that copper. No warehouse held that copper quietly waiting. It wasn't simply unavailable, it was impossible to get. In 1942, copper was the oxygen of the war. Everywhere you looked, it was disappearing into military production, battleship wiring, aircraft generators, tank radios, artillery fire control systems, thousands of miles of communication cable, millions of brass cartridge cases. Copper wasn't just important. It was the material that kept the entire American war machine breathing. The War Production Board had already rationed it heavily. Factories fought for scraps. Contracts were delayed. Orders were reassigned. Ammunition programs were begging for metal. And the Manhattan Project, still a mysterious secret program with no name the public could know, was now asking for a metal more precious than money: time. The engineers considered alternatives. Steel was useless. Aluminum couldn't carry the current. Brass was even worse. There was only one metal that could replace copper without destroying the Calutron's performance: silver, the most electrically conductive element on Earth, even better than copper. In fact, it was so conductive that 11 parts silver could replace 10 parts copper, a slight but critical efficiency advantage. Nichols and Marshall stared at the numbers. If they replaced the 5,000 tons of copper with silver, they would need around 5,500 tons, a terrifying amount. But silver, unlike copper, wasn't being consumed in war production. And there was only one place in America where thousands of tons of pure silver existed in uniform bars: the United States Treasury. Specifically, the West Point Bullion Depository, stored in neat, gleaming stacks, guarded tighter than gold, officially backing the nation's currency, belonging to the American people. And the Manhattan Project needed to melt it, not borrow a few bars, not temporarily reassign a reserve. They needed to take silver, the literal wealth of the country, turn it into billets, extrude it into long strips, and wind those strips into enormous electromagnetic coils, all for a machine that might not even work at industrial scale. The idea was so extreme that when first suggested, some believed it was a joke. Others thought it was a clerical error. Borrow tons of silver, melt it, turn it into wire, ship it across the country? But Nichols wasn't laughing, and neither was the Manhattan Project. They had crossed the line where sanity, logic, or standard procedure mattered. All that mattered was time. If silver could carry current better than copper, then silver was the only option. And so the engineers made the decision. They would ask the United States government to hand over a portion of its national wealth physically, literally, for a weapon that did not yet exist. Nichols prepared himself. He had to return to the Treasury, not with 6,000 tons, as he once said, but with a number so large that no one had ever asked for it before: 14,700 short tons of silver. Enough to build a machine the size of a factory, with magnets the size of houses, in a valley no one had heard of. And that request would set in motion one of the strangest industrial operations in American history. To the Manhattan Project, the numbers were almost abstract. 5,000 tons of copper replaced by 5,500 tons of silver, coils the size of locomotives, magnetic fields powerful enough to rip tools out of workers' hands. But nothing made the scale real until the silver itself began to move. Nichols didn't sleep the night before the first transfer. War or not, this wasn't scrap metal. This was the nation's wealth, thousands of tons of it loaded onto trains under armed guard, destined not for safekeeping but for furnaces. The bars stored at the West Point Bullion Depository were uniform, 1,000 troy ounces each, about 31 kilograms, stacked in endless rows, silent and perfectly still. Every bar accounted for, every bar weighing the same, and every bar about to vanish into a machine no civilian was allowed to know existed. The transfer orders were signed. Guards were assigned. The shipments began. Train after train rolled out of West Point, carrying silver to the first stop in a long industrial journey, the Defense Plant Corporation facility in Carteret, New Jersey. Here, under strict security, the bars were melted down. The heat in the furnaces was intense enough to turn solid wealth into liquid metal. Molten silver poured into molds, forming cylindrical billets, the intermediate shape needed for extrusion. Workers treated the billets with a reverence normally reserved for religious artifacts, not because of the bomb, not because of the secrecy, but because they understood the stakes. Every ounce had to be tracked. Every ounce had to be returned after the war. Lose even a handful of filings, and someone had to explain why. Once cooled and inspected, the billets were shipped again, this time south to Phelps Dodge in Bayway, New Jersey, one of the few industrial facilities capable of extruding metal to the extreme dimensions required. Here, the billets were forced through massive steel dies under enormous pressure, stretched into long, gleaming strips, 625 inches thick, 3 inches wide, 4 feet long. Silver in this form no longer looked like treasure. It looked like raw industrial muscle, and that transformation was exactly the point. The Manhattan Project needed hundreds of miles of this material, enough to wind coil after coil after coil, and Phelps Dodge delivered. In total, 258 railcar loads of silver strips left the facility, each shipment documented to the fraction of a troy ounce. Next destination: Alice Chalmers, Milwaukee, Wisconsin. If Carteret was the furnace and Bayway was the stretching press, Alice Chalmers was the heart of the operation where the silver strips were transformed into Calutron coils, the massive magnets that made the entire separation process possible. Inside enormous fabrication halls, engineers wound the silver strips onto gigantic mandrels. The coils grew layer by layer, ton by ton, into structures so heavy that ordinary cranes strained to lift them. Each coil was sealed inside a welded steel casing, designed not only to protect the silver but to withstand the brutal magnetic forces the calutrons would unleash. Workers joked that the casings were coffins, solid, heavy, impossible to open without heavy machinery. But once sealed, the silver inside became invisible, unrecognizable, and that was a blessing, because once the magnets were encased and painted, they no longer looked like precious metal, just industrial equipment. And that meant they could be shipped without armed guards. Flatbed rail cars carried them across the country, unprotected, as ordinary freight. To anyone watching from a station platform, they were just another shipment of bulky factory hardware. Their final destination: Oak Ridge, Tennessee, the secret city rising in the hills, a place that didn't appear on any map. Meanwhile, all across the system, the Treasury demanded monthly accounting. Nichols filed reports down to the troy ounce. Any discrepancy, however small, triggered immediate investigation. Floor sweepings were collected. Drill chips were saved. Even oily rags used during winding were stored for later extraction. This wasn't just construction. It was stewardship, an industrial pilgrimage wrapped in secrecy, mathematics, and trust. By the time the last coil arrived at Oak Ridge, the United States had done something unprecedented. It had taken a national fortune, melted it, reshaped it, shipped it through half a dozen states, and turned it into the nervous system of the most ambitious machine ever attempted. And the machine wasn't even turned on yet. By the time the silver coils arrived in Tennessee, Oak Ridge was no longer just a construction site. It was a new kind of city, a secret city built at a speed no one had thought possible. The government had chosen Bear Creek Valley, an isolated stretch of land surrounded by ridges. Those ridges weren't chosen for scenery. They were chosen because if something went wrong, an explosion, a criticality accident, a magnetic catastrophe, the mountains might contain it. Oak Ridge grew into a sprawling industrial labyrinth, 825 acres for the electromagnetic plant alone, with nearly 80 acres of indoor floor space, workshop after workshop, warehouses, machine halls, power stations, cooling towers, hundreds of buildings rising from the mud. But the real giants, the heart of the operation, were the Calutron racetracks, wings. From above, each racetrack looked like an enormous oval. Inside that oval were rows of vacuum tanks, each one a steel cylinder weighing 14 tons. Around each tank, the newly arrived silver coils wrapped like metallic muscles. These machines weren't elegant. They weren't pretty. They were industrial beasts, loud and temperamental, vibrating with power. Inside each vacuum tank, the real separation happened. Uranium tetrachloride, a greenish, corrosive compound, was vaporized and then ionized. The ions accelerated inside the curved chamber, flying into the path of the giant silver wound magnets. When the magnets pulsed, the beam bent. Heavier U-238 atoms curved less. Lighter U-235 atoms curved more. They struck different collectors, forming faint smears of enriched material. Each smear represented hours, sometimes days, of continuous operation. But the physics that worked perfectly in Lawrence's laboratory became unpredictable and violent at scale. Almost immediately, the engineers at Oak Ridge discovered that nothing about the full-size Calutrons behaved the way it was supposed to. The vacuum tanks shifted under intense magnetic forces, drifting up to 3 inches out of alignment. A 3-inch shift might not sound like much, but inside a precision magnetic field, it was catastrophic. Misalignment meant the ion beams smeared across the collectors. It meant the enriched material scattered. It meant days of work could vanish into useless residue. The engineers scrambled to anchor the tanks more securely. New braces were installed. Supports were redesigned. Entire tanks were jacked back into position while work crews held their breath. Then came the moisture problem. The silver coils were masterpieces of purity and conductivity, but they were also sensitive. Humidity inside the casings caused short circuits and rust, forcing magnets to be dismantled, cleaned, and rewound. Every time a magnet failed, it took hours of manpower and days of lost production. But the worst enemy of all was something the scientists jokingly called gunk. When uranium tetrachloride vaporized inside the vacuum chamber, impurities condensed on the walls and drifted into the beam slits. Dust, residue, microscopic debris. It clogged apertures, blocked ion paths, defocused beams, melted collectors. Every particle of gunk threatened the entire process. Engineers fought back with new cleaning procedures. They developed ways to wipe down interior surfaces without contaminating the precious silver or the collectors. They improvised tools, filtered contaminants, and built new maintenance routines from scratch. Then there was the heat. Even though the ion beams were tiny microamps, they produced intense, localized heating over hours of operation. Collectors warped, metals deformed, beam alignment drifted. Cooling systems were added. Monitor panels changed. Operators learned to adjust settings in real time to compensate. And through it all, the silver had to be protected. Every drill hole required paper underneath to catch filings. Every wiped surface produced rags that had to be burned and recovered. Even the floorboards beneath the machines years later would be ripped up and incinerated to extract microscopic particles of missing silver. Nichols filed monthly accounting reports to the Treasury with military precision. Every troy ounce was tracked. Any loss was unacceptable. It was engineering under pressure, pressure from physics, from time, from secrecy, and from the unimaginable cost of failure. But despite the chaos, the breakdowns, the short circuits, the drifting tanks, the clogged slits, the melted collectors, one truth became clear. The machines were learning, the engineers were adapting, and Oak Ridge was crawling, inch by inch, toward becoming the first factory on Earth capable of producing bomb-grade uranium. What no one expected was that the next breakthrough wouldn't come from the scientists or from the engineers, but from the people hired to operate the machines. Ordinary people, mostly young women, many of them barely out of high school, and they were about to outperform the PhDs who built the system. By early 1944, after months of fighting breakdowns, misalignment, heat damage, and mountains of gunk, the first Alpha racetrack at Oak Ridge finally came online. It wasn't perfect, it wasn't stable, but it worked, and now it needed operators. Not scientists, not PhDs, not the men who designed the Calutrons. Operators. The Manhattan Project turned to Tennessee Eastman, a chemical company contracted to run the separation plant. Their task was monumental. Recruit and train thousands of workers to operate machines that were highly technical, unbelievably sensitive, and absolutely secret. The talent pool? Young people from the rural communities surrounding Oak Ridge, mostly women, many just out of high school, daughters of farmers, mechanics, and miners. Some had never seen a factory before stepping into WWII, but secrecy dictated the rules. No one could know what the Calutrons did. No one could know what the needles meant. No one could know what enriched uranium was. And absolutely no one could know they were helping build the world's first atomic bomb. So the training was brutally simple. Keep the needles in the green zones. Turn this knob if the needle drifts. Turn that one if it drifts the other way. Do not ask questions. His barked. The control panels looked like something from a surreal machine, cathedral walls of dials, gauges, toggles, and lights. Each gauge monitored a part of the beam: temperature, current, vacuum pressure, magnetic field stability. A tiny fluctuation could ruin hours of production. A wrong adjustment could cost days. But the Calutron girls didn't know any of that. They only knew the rules. Dial A must stay between these marks. Dial B must never fall below this number. If this light blinks twice, turn knob C exactly 1/4 turn clockwise, nothing more. And yet, to the shock of everyone involved, the results were phenomenal. At first, the PhD physicists from Berkeley, the men who had designed the Calutrons, operated the machines themselves to establish procedures. They worked carefully, analytically. If a dial shifted, they paused to understand why. If a reading fluctuated, they investigated the underlying cause. They were brilliant. But brilliance wasn't what the machines needed. The Calutrons needed speed, consistency, immediate reaction. So when the scientists handed control to the new Tennessee Eastman operators, Nichols began comparing production logs. The numbers didn't make sense. Output was up. Beam stability was better. Recovery rates improved. Downtime dropped. The young women were outproducing the PhD physicists. Nichols didn't believe it at first. He checked the logs. Then the supervisors. Then the shift reports. The pattern held, so he told Ernest Lawrence. Lawrence refused to accept it. How could young women, many without college degrees, some barely out of high school, operate the Calutrons better than the men who had built them? To settle the debate, they organized a competition. Lawrence's scientists on one side, the Calutron girls on the other. Same machines, same time window, same production targets. It wasn't even close. The girls won, not by luck, not by accident, but because they followed instructions with perfect discipline. When a needle drifted, they corrected instantly, without hesitation, without theorizing, without losing time chasing explanations the machine didn't care about. The scientists couldn't help themselves. They needed to understand what was happening inside the beam, why it drifted, what physics caused the shift. In a laboratory, that instinct was invaluable. But on the racetracks, every second lost was uranium lost. Execution beat understanding. Nichols later said it plainly. They were trained like soldiers not to reason why. They walking to stride. They didn't need to know the physics. They needed to keep the machines alive. And they did, hour after hour. Shift after shift, day after day. They kept the needles steady. They kept the beams stable. They kept the Calutrons running at peak efficiency. The fate of the Manhattan Project and the world's first uranium bomb began resting in the hands of young women who weren't allowed to know what they were building. Only after the war would many of them learn the truth. They had been separating uranium-235. They had been fueling the atomic bomb. They had been playing a role the world would feel in Hiroshima. Some felt pride. Some felt horror. All were astonished. But inside WWII, before they knew any of that, they were simply doing their jobs, executing with a precision that even the scientists could not match. And because of their work, the next stage of the project, producing enough enriched uranium for a weapon, suddenly became possible. By mid-1944, WWII had become something no one on Earth had ever seen before. A fully functioning factory for separating isotopes, a process so delicate it normally required precision instruments on a laboratory bench, now scaled to the size of buildings. The Alpha racetracks did the first pass. They took natural uranium and increased the fraction of U-235 tenfold. Then the partially enriched material moved to the Beta racetracks, where the beams bent sharper, the collectors grew narrower, and the tolerances became brutal. This multi-stage chain Alpha to Beta was the only path that led from raw uranium ore to bomb-grade uranium metal. And every step was agony. Production never accelerated as quickly as the Manhattan Project wanted. Breakdowns were constant. Alignment issues returned whenever magnets heated. Collectors warped. Vacuum seals failed. Gunk crept back in like a recurring illness. Every piece of the system had to be coaxed, maintained, cleaned, and corrected. But the Calutron girls stayed on it. Shift after shift, they kept needles in the green zones. Their focus, their discipline, and their relentless steadiness became the quiet heartbeat of the entire operation. By late 1944, the racetracks were finally running in a rhythm, an imperfect rhythm, but a rhythm nonetheless. Production increased. Losses decreased. The enriched material moved steadily from one building to the next. A year earlier, even the most optimistic scientists doubted Oak Ridge could ever produce enough U-235 for a weapon. Now, the numbers were climbing. The engineers still fought the machines every day. A beam would collapse in the middle of a shift. A collector would melt. A tank would drift an inch and force a shutdown. But the teams adapted faster each month. Then came 1945. The war in Europe was ending. Germany had surrendered, but the war in the Pacific raged on, and the pressure on the Manhattan Project increased to nearly unbearable levels. Every gram of U-235 mattered literally. For every kilogram of bomb-grade material, tens of thousands of kilograms of natural uranium had to be fed through the Calutrons, and every operational hour counted. By the summer of 1945, after years of failure, rebuilding, refinement, and thousands upon thousands of hours of operation, Oak Ridge had done what many believed impossible. They had produced enough highly enriched uranium for a single weapon. That uranium, about 64 kilograms, enriched to roughly 80% U-235, was sent to Los Alamos, where it became the core of the first and only uranium gun-type atomic bomb ever built, Little Boy. On August 6, 1945, at 8:15 a.m., a B-29 bomber named Enola Gay released Little Boy over Hiroshima. The bomb detonated with the force of 15,000 tons of TNT. 5 square miles of the city were destroyed. An estimated 70,000 people were killed instantly. Tens of thousands more would die from injuries and radiation across the following months. 3 days later, a second bomb, Fat Man, a plutonium implosion device, struck Nagasaki. On August 15th, Japan surrendered. World War II was over. For the scientists and engineers who had worked at Oak Ridge, the moment was overwhelming. They had been racing physics, time, and the Axis powers with a machine held together by hope, ingenuity, and tens of thousands of hours of operator discipline. Only after the surrender were many workers told the truth. The strange green needles they had been watching, the mysterious adjustments they had made by the thousands, the gunk they had scraped out of vacuum tanks. All of it had been part of building the components for the weapon dropped on Hiroshima. Some felt pride. Some felt guilt. Some felt both at once. There was no easy emotional conclusion because history rarely offers one. But the fact was undeniable. Oak Ridge had succeeded. The Calutrons had worked. The engineers had done the unthinkable. And the war had ended partly because a secret machine in the Tennessee hills had quietly separated enough uranium atoms to build one bomb. That success, however, came with a final responsibility, one that would take years to complete, because the Manhattan Project had borrowed nearly 15,000 tons of silver, and it all had to be returned. The war was over. The cities of Hiroshima and Nagasaki lay in ruins. The world had entered the nuclear age, and every part of the Manhattan Project now faced a final, uncomfortable question. What happens to everything we built? For Oak Ridge, the answer was clear, but staggering. The electromagnetic separation process, the entire Calutron system, was no longer needed. Scientists already knew another method. Gaseous diffusion could produce enriched uranium faster and far more efficiently. Electromagnetic separation was brilliant, but it was slow, expensive, and energy-hungry. Its purpose had been singular and temporary: produce enough U-235 for one bomb. Now, that purpose was complete, and that meant the machines had to be dismantled, not cleaned, not stored, dismantled piece by piece, until every component that came from the Treasury could be accounted for down to the last fraction of an ounce. This was not optional. It was a promise. The moment the Treasury agreed to lend the silver, long before the magnates were ever wound, they made one rule absolutely clear: every single troy ounce must be returned. And so began one of the most meticulous industrial operations in American history. The Calutrons went dark. The racetracks, once glowing, humming, vibrating with power, became quiet circles of steel and concrete. Workers moved through the buildings with tools instead of control sheets. The same machines that once pushed the boundaries of physics were now being undone with wrenches, hammers, and torches. But the challenge wasn't simply taking them apart. It was recovering the silver. The magnets had to be cut open, their casings split apart, their massive coils unwound carefully to avoid damaging the metal. Strips of silver, once perfectly formed, came out bent, twisted, darkened by heat and years of operation. Every strip was cleaned. Every strip was weighed. Every strip was counted. And the collectors, the tanks, the beam chambers, the high-voltage terminals, everything that had been near the Calutrons had to be treated as potential sources of microscopic silver loss. Workers wiped surfaces with cloths. Cloths were burned. Ashes were sifted. Residues were chemically processed. Floorboards, the literal floors beneath the machines, were ripped up and incinerated because silver dust had settled into the cracks. The ashes went through filters fine enough to capture particles invisible to the human eye. Even vacuum lines and maintenance rags, anything that had ever touched a silver component, were treated like treasure. It was exhausting, detailed, unglamorous work, but the stakes were real. The Treasury wanted its metal back. Every month, Kenneth Nichols sent accounting reports, just as he had during the war. But now the reports tracked recovery rather than distribution. As the months passed, then the years, the numbers added up. Out of 430 million troy ounces of silver loaned, the Manhattan Project recovered all but 155,645.39 troy ounces, less than 0.036%, for a process involving molten metal, rail shipments, fabrication, huge electromagnetic forces, corrosive chemicals, and constant wear. The loss was microscopic, almost unbelievable. And yet that remaining fraction, roughly 4.8 tons, was considered acceptable. Some of it had vaporized. Some had chemically bonded into materials that could never be separated. Some had simply disappeared into places no extraction method could reach. The Treasury signed off. The debt, one of the largest internal transfers in American history, was closed. But the story didn't end immediately. Even after the accounting was complete, even after the racetracks were stripped bare, even after most of the site shifted to new missions, a final batch of silver remained in use. The last 67 tons stayed in service as industrial components until 1970, almost 30 years after the loan began. Only then were they swapped for copper and returned to the Treasury, officially closing the final chapter of the Calutron silver. It was a strange end, a quiet end. No celebrations, no announcements, just a simple fact: 14,700 tons of silver had gone into a secret wartime machine, and almost all of it came back. The Calutrons were gone, the racetracks silent. But the legacy of what Oak Ridge accomplished could not be dismantled so easily, because the machines had succeeded, and because their success had changed history. When the last coils were unwound, when the final ounces of silver were counted, and when the racetracks of Y-12 finally fell silent, it seemed as though the Calutron era had ended. In one sense, it had. Its purpose, a single, urgent one, was complete. But legacies rarely disappear just because a machine is turned off. What happened at Oak Ridge left marks far deeper than the concrete pads where the Calutrons once stood. Many of those marks are physical, many are technological, some are ethical, and all of them continue to shape the world long after the silver returned to the Treasury vaults. A technology that outlived the machine. The Calutrons themselves became obsolete almost immediately after the war. Their enormous appetite for electricity and manpower made them impractical for peacetime production. Gaseous diffusion, far more efficient, replaced electromagnetic separation almost overnight. But the principle behind the Calutron did not die. The physics that Ernest Lawrence leaned on, the bending of charged particles through magnetic fields, became the foundation of one of the most important scientific tools of the modern age, the mass spectrometer. Today, mass spectrometers are everywhere. Medical research, environmental monitoring, forensic science, planetary exploration. We do us, to us, to us, to n. The machines that diagnose diseases, analyze toxins, and study the chemistry of stars all use the same fundamental idea that powered the Calutrons. Ionize particles, bend them through magnetic fields, separate them by mass. It's an elegant echo of wartime desperation transformed into peacetime discovery. A facility that never stopped being important. Oak Ridge did not disappear with the Calutrons. The site evolved, changed, and adapted. Today, Y-12 is known as the Y-12 National Security Complex, part of the Department of Energy's National Nuclear Security Administration. It no longer enriches uranium. That part of the mission has long since moved to other technologies and other facilities, but its new role is no less critical. Y-12 builds and maintains components for every nuclear weapon in the United States arsenal. The same valley that once housed silver-wound Calutron coils now handles the materials that sit at the core of modern nuclear deterrence. The mission changed, the technology changed, but the stakes remained enormous. A lesson in the extremes of wartime engineering. The story of the Silver Loan is, on the surface, a logistical oddity, almost a curiosity. A nation borrowing its own wealth to build machines that looked more like industrial sculptures than scientific instruments. But deeper down, the story reveals something essential about wartime innovation. When the stakes are high enough, nations attempt things they would never dream of in peace. Borrowing 14,700 tons of silver wasn't efficiency. It wasn't strategy. It was urgency, a desperate answer to a desperate question. It took physicists willing to imagine the impossible, engineers willing to solve problems that no textbook covered, workers willing to operate machines they didn't understand, and a government willing to sacrifice treasure for time. The result was imperfect, expensive, often chaotic, but undeniably effective. The human legacy. Perhaps the deepest mark left by the Calutron era is not in the technology or the machines, but in the people. The young women who sat at control panels without knowing what they were controlling. The machinists who shaped silver coils with obsessive precision. The engineers who rebuilt failing magnets late into the night. The scientists who swallowed their pride after losing a production race to teenagers. For many, the truth of what they had been part of only came after Japan's surrender, and the emotions were complicated. Pride, shock, guilt, awe. But one lesson echoed through every memory. Success did not belong only to the scientists who understood the physics. It belonged equally to the ordinary people who executed the work. In that sense, the Calutron girls stand as one of the clearest reminders of the Manhattan Project's hidden reality. Understanding builds the design. Execution wins the war. The final echo. The silver returned. The racetracks dismantled. The Calutrons scrapped. But the world they helped create, the nuclear world, remains. Every mass spectrometer, every nuclear weapon, every scientific breakthrough that relies on separating atoms by mass, every element of national strategy shaped by nuclear deterrence, all of it traces back, in a quiet line, to that August morning in 1942 when a young officer walked into the Treasury and asked for a number no one could comprehend. Little did they know, 14,700 tons of silver would become the metal that pushed humanity into the atomic age.